this computer. All right, hello, welcome back. I hope everybody's doing well. We got about 20 on the call so far, and that's great. I see people are using the YouTube videos and going and reviewing afterwards, after class. That's great. I'm glad to see that. And so also, one of the things is you should have received 2 emails from me today. One was the group activity email, which has the one we'll be doing this afternoon. The other one should be the chapter 19 review table, reactions table. And so what I want to do today is also, I want to kind of go through those 2 tables and kind of show you how to use them and how I design them. And then that kind of will help you use it as a study aid. But also, while I'm doing that, I want to draw attention to like the 3 most important things about chapter 18 and the 3 most important things about chapter 19. And so that'll be kind of summarizing all of this stuff and getting us ready for the activity. The activity really culminates everything we learned in 18 and 19 together, but we have the challenge where we make rings. And that's where the 3D spatialization gets a little challenging. So I think I've laid out a plan for us to help understand how we get the rings, how to count the rings, and know which size ring we're going to make from this exercise, okay? So that's where I'd like to go with this particular class day. Excuse me. So administration, of course, this is our last class for the week. We do not meet tomorrow. All we have is our online exam. Homework is due at midnight tonight. After that, you can review it. Our group project will start at 1 o'clock sharp, and then I'll put you into breakout rooms, and then we'll go ahead and see how long that goes. And then, you'll receive an email on Monday morning with our new Zoom room. We have 2 quick chapters, which is chapter 20, which is amines, and then we have a part of chapter 21, organometallic reagents. And I want to show you, a couple different things about that. And then we'll have at least 1.5 class periods to talk about reviews. And part of that review is to give you kind of some ideas on how to study for the exam. And then, of course, our exam is next Thursday. So make sure you have that blocked out on your calendar, not at our regular scheduled time. It starts at 2 and goes to 4:30. Okay, so that being said, that's all our administration. Any questions about that right now? Okay, good, good. So let me go ahead and pull up my table for number 18 and start with that first. Actually, let's start with 19 first, because I just finished that and sent that out. And so I'm going to go ahead and share my screen. And it should be that one right there. Okay, so what you should see as part of our shared screen is this table here. And this is called the chapter 19 reaction table. And so what I've done is I've broken it down just like the chapter 18, kind of the name that it would have, to the quick name to get associated with it. Oh, that's a great idea. Before we get into chapter 19, a suggestion was made that, everybody has a bad week sometime. And in a long semester, I would have an opportunity to drop the lowest exam. Unfortunately, we don't have that luxury here. So one of the suggestions was made, if your final exam grade is higher than the one of your lower exams, that I could replace it with that higher grade. And so the idea would be that, so you have an opportunity to, have a bad week, but still make a good grade in the class. So is there let me see if I can get my polling feature here. Polling. I'm going to add a question to the polling thing, and let's see. Let me see. So if you want to do this, if you think this is a good idea, go ahead and come on. Why is it opening up 7 meeting rooms here? Okay.
Wait, Dr. Irvin, would there be a reason why we wouldn't want that to happen?
I can't think of a reason.
Okay.
It's not going to replace it if if the exam grade's lower. It's only going to replace it if it's higher.
Of course. Okay.
So exam replace lowest exam with final if higher. See, I need to kind of poll people because it's not in the syllabus like that. So I need to make sure that at least I have a consensus on that. So save and launch poll. I'm going to go ahead and launch the poll. And so if if we get enough people, greater than 50% of the people who are here, and there's 28 people here, then we can have this motion pass, and I'll include it in the, I won't necessarily change the syllabus, but I'll have a record that we've talked about this and we've agreed to this change. So, and so that way, everybody has been informed, and then I'll send out an email saying we took a vote on it, and so this will be happening. So I like the concept because, everybody has a bad week. I understand that. Everybody has, good days and bad days. And so this gives us an opportunity to give us our best foot forward and get our best overall grade. So, okay, I think of those voting, most of them voted yes or abstained. So, so I will end the poll and go ahead and write that down. And I will, let's see, stop that. All right. Okay, let me go ahead and stop share and close the poll. All right, great. Thank you very much. I forgot about that. The curve should be fine as well. The homeworks, the overall average on the homeworks is pretty good. So I only want to do that for the final exam. Share. Okay. So great. Thank you for reminding me about that. The final we will be taking is not the ACS final, but it is similar to the ACS final in the fact that it'll have 70 questions. It'll be multiple choice. Imagine the questions we've already had. They're going to be those similar style of questions, obviously not the exact same question. The ideas are that, you can, identify the functional groups and talk about the mechanisms and look at those different things. So it will not be the ACS final. However, it will be similar to it. Okay. All right, so let's go ahead and look at this chapter 19 reactions. So what I've done is I've broken it down into the different named reactions and reminded you what the starting materials for each of the reactions are, okay? So in the case of the claisen here, all we need for a claisen reaction is an ester, okay? And remember, the first step is always to deprotonate that material. So in the case of the esters here, I have the CH2 listed here because we need at least one hydrogen here, one acidic hydrogen, to be able to make our enolate. Once we form that acidic hydrogen, it actually attacks the carbonyl of another group, giving us that tetrahedral intermediate, but we have the alkoxide able to be a good leaving group. And therefore we regenerate our carbonyl compound. So the product is always a beta keto ester, okay? So we will always get a beta keto ester from that. And if there is, only one place that has acidic hydrogens and only one place that has a carbonyl, the reaction's fairly straightforward. It is, just add the pieces together and go ahead and do it. Now, if you want a very clean reaction, you can get a very symmetrical molecule, a very unsymmetrical molecule by doing what we call the cross claisen. And that's where one of your materials has a carbonyl compound on it, specifically an ester. Now, the reason we want an ester there is so that we can eliminate that alkoxide and generate our ketone from that species, okay? So we know that the compound without the alpha hydrogens is the one that's going to be the ketone, okay? The one with the alpha hydrogens is the one that's going to be the ester, okay? So it's very clear at which part reacts, okay? Both reactants of the claisen reaction are esters. Yes, yeah, that is true. Okay, so there are some ways that you can do, like when we do aldols, there are opportunities to use other carbonyl compounds other than aldehydes and ketones. And we call those acylations because usually we have chloride as a lead group. But in the Claisen, it's always esters. And our product is always a beta keto ester. Okay. So the only weird modification of that would be what we call the Dieckmann. And the Dieckmann is just an intramolecular ester, Claisen, and that intramolecular Claisen still ends up with a beta keto ester, but we also have a ring, okay? So in our exercise today, we'll start talking about how we know what size ring we're gonna make. And so the way we'll actually do that is that we'll have to figure out where we can pull off a hydrogen, and then start numbering from that enolate ion over to the next closest carbonyl. And once we find that next closest carbonyl, that's going to tell you the size of the ring we're forming. Okay, so we'll do that in the activity, but that's kind of a heads up on how to look for what sizes we can make. And while in theory you technically can make bigger and smaller than 5 and 6 membered rings, those are predominantly the products we form, if at all possible. If you have a choice between a 4 and a 6 membered ring, it's always going to make the 6 membered ring. Okay. So that's the Claisen. Esters, Claisen, and we can do it with or without alpha hydrogens if you want to do a cross Claisen. Okay. Now, when we move away from esters and go to aldehydes, we have what we call the aldol addition. Okay. So if it's just an aldehyde, it's the aldol addition, and we end up with a beta hydroxyaldehyde. Okay, note the key here on my conditions list is base with no heat. Okay, no heat, because if we heat, we have an opportunity for an acid or base catalyzed dehydration to form an alkene. And that's a different reaction. We'll talk about that next. But so when we have an aldehyde, we always get a beta hydroxyaldehyde. But if we have a ketone, we end up with a beta hydroxy ketone. Okay, so and there should be another R group on this OH right here. So there's always going to be, there's an error on my slide here. There should be an R group. This R prime should be on this OH group here. So I'll correct that after class and send it out, but it needs, yeah, R. Okay. So, and again, the idea is we'll make our enolate on one molecule and it'll go and attack the carbonyl on the other, but it doesn't reform our trigonal planar, our sp2 hybridized carbon without the use of heat. Okay, so we can do that same thing with the cross aldol, where we have one of our substrates has no alpha hydrogens, and that means you had to form your enolate from one compound. So you know exactly where your aldehyde or ketone is going to be, because that's the one that had the alpha protons available to it. You know, what if you started with a ketone on this enolate with your hydrogens here, then you're going to have a ketone in your product. If you started with an aldehyde where you made your enolate, you'll have an aldehyde in your product. Okay, so you can be very careful about how you do things. In addition, this is also the one where you can actually displace a chloride on here. That was that unusual reaction where you can start with an acid chloride and it'll displace that acid chloride and give you a different product. Okay, but the idea here is, again, base with no heat, and that gets you to your beta hydroxyaldehyde or ketone. Okay. So then, of course, we have an opportunity for an intramolecular aldol. There's a Z on the end of here because that could be if it's a dialdehyde, you can have a hydrogen here. If it's a ketone aldehyde, you'll end up with whatever your R group is at Z. So I actually ended up putting Z in the right place on this one at least, so that's great. We'll always end up with a beta hydroxyaldehyde or ketone. And again, it'll typically form 5 and 6 membered rings. It can be forced to make other rings, but we rarely see it. Okay. So, and then, so those are the aldol addition reactions. Okay. So in the aldol additions reactions, we don't end up with two carbonyl compounds because we don't have a good enough leaving group yet, okay? So the next variation of the aldol reaction is when we add heat at the end. If we add heat at the end, we end up with our aldol condensation. Remember, our condensation is called that because it removes a small molecule that condenses out of the reaction. And so in that case, we have the removal of an OH from that beta position and a hydrogen from the alpha position, giving us a conjugated, unsaturated aldehyde or ketone. It'll always try to form the conjugated form because the conjugated form is more thermodynamically stable. Okay, so what we'll see here is we'll always get this alpha beta unsaturation, which is alpha carbon, beta carbon unsaturation, and it's always going to be in conjugation with the carbonyl compound. And again, this can be a ketone or an aldehyde. It's the same reaction mechanism. Okay. Okay, that leads us to, so that's all of the condensation reactions. You know, so we covered esters, we've covered aldehydes, and we've covered ketones, okay? Now we have another set of reactions that are complementary to these, which are the conjugate addition reactions. And the reason it's complementary is we actually make these alpha beta unsaturated ketones from our aldol condensation reaction. So we can use it as the first step in a multi-step synthesis to get to these reactions. Okay, so when we talk about these alpha beta unsaturated aldehydes and ketones, we're looking at it from the perspective of it's conjugated, therefore it can do a 1,2 addition or a 1,4 addition. And when we do a 1,4 addition, the enol will be rearranged to give us our carbonyl compound back, okay? So the main difference between whether or not it attacks the carbonyl or attacks that beta carbon position is how strong is your nucleophile. So strong nucleophiles like hydroxide and Grignard reagents and alkyl lithium reagents, those are going to add across that carbonyl, giving you that alcohol species right here. So when we have those strong nucleophiles, we end up with this alcohol on turning the carbonyl into an alcohol, okay? So if instead you can wait around with a weak nucleophile, you're going to get that beta addition. And so we end up with getting our double bond is getting the nucleophile is going to be on that beta position, and then we add a hydrogen to that alpha position. So we end up with a beta nucleophile, some kind of carbonyl compound. Okay. So, and there's a, we can, again, have this carbonyl compound be an aldehyde, a ketone, an ester, or even a cyano group will work here, because as long as it's an electron withdrawing group here, it will do that conjugated beta addition of a weak nucleophile. Okay. So the enolate derivative of that is what we call the Michael addition. That's where we create our enolate as our weak nucleophile. And so we can end up getting these really multifunctional species from it, but it's the same reaction. This is where our nucleophile was generated here, and we're going to have attachment at our beta position. Okay. Now, once you get to here, if you have esters, you can hydrolyze, you can decarbonylate, you can do additional reactions on it. But the first step is exactly the same, beta addition of our nucleophile, and then an alpha addition of a hydrogen. So it's the same reaction, it just looks a little more complicated. Okay. So, excuse me, the next kind of alpha beta addition we can do is using the trapped enol form. So this is the enamine, right? So we've trapped it in this enol form, and that makes that these electrons here in this trapped enamine, the nucleophile that comes out and does that beta addition. Now notice this is one of the interesting things. Before we had a carbonyl that was 2 carbons away, or carbonyls that were 1 carbon away. In this case, this is the first reaction where we can selectively choose our carbonyl to be 3 carbons away from our starting material. Okay, so this is a key that I want to kind of draw attention to, is that this is, you know, we've done it where we have things at the alpha and things at the beta. Well, we've actually extended it one more. So we have 3 carbons in between these 2 carbonyls. And again, R can be hydrogen, it can be an ester, it can be a ketone. Okay, so then the last 2 reactions are a little bit more complicated, but if you line them up correctly, you will get the right product most of the time. And that is the Robinson annulation and the Mannich reaction. In the Robinson annulation, it starts with that beta addition of an enolate to a conjugated aldehyde or ketone. I'm sorry, it has to be a ketone. So we have beta addition to our conjugated ketone by an enolate, okay? And so it can stop there, but however, if you add a little more base, you can deprotonate. You have to have a proton here on this alpha carbon on the other side. If you deprotonate this, it becomes the enolate and will attack the carbonyl nearby, always forming a 6-membered ring. And notice the double bond moves from where we did the Michael addition up here to the opposite direction to where we created that new bond by first adding to this carbonyl, giving us an alcohol, and then doing a dehydration to regain our double bond. So if you follow the, this is in red and blue, but I'm hoping they're also shaded differently in the grayscale version. But it just kind of shows you that we want to follow where this double bond goes. Just like when we followed where the double bond went when we had the Diels-Alder reaction, in the Diels-Alder reaction, the double bond always ended up between the diene alkenes. And so we could follow where the carbons started by where the double bond was at the end. Okay. All right, and then our last reaction here is what we call the Mannich reaction. And the Mannich reaction is unique in the fact that we end up adding a CH2 and an amine to our ketone, okay? And we do it in a stepwise fashion because we add an aldehyde to a secondary amine, creating our intermediate iminium anion. That is then attacked by the carbonyl, the enolate made by the alpha hydrogen here. And so this carbon is from formaldehyde. This nitrogen is from our amine. And then the remaining 3 carbons or other carbons are from our initial ketone. Okay. Now there's a lot of examples where these are cyclic, and so you can end up with cyclic on both sides or not. But you know, it can be non-cyclic systems, but the cyclic systems are really pretty when we draw them out. Okay, so that is reviewing the reactions in chapter 19 and how I think you should look at the table and look at kind of what the complications are in this thing. For example, you know, without heat, we have aldol additions. With heat, we have the aldol condensation. 5 and 6 membered rings, look for 5 and 6 membered rings. And then the spacing of where our materials are. In the aldol and the claisen, we tend to have beta hydroxy or beta keto compounds, okay? In the Stork-enamine reaction, we end up with it in the delta position. So we have alpha, beta, gamma, delta. So it's actually in the 4th carbon over, or has a 3 carbon spacer on it. So that's unique to the Stork-enamine reaction. Okay, let's see what we have here. So that is my summary of chapter 19. Any questions on that? Okay, so let me go ahead and just pull up. Remember, you also have this review of reactions from chapter 18. And this is a good complement to what we already had before. It's the formation of our enolates, the different reactions that those enolates can do up to before the condensation reactions. Notice attack with nucleophiles is similar. These E2 eliminations here, where we can create those, this is how we get those conjugated ketones by another method, especially if we have something like a halide here or something that makes it a good leaving group. And then the malonic acid ester synthesis is you're going to add a CH2 and a carboxylic acid. So you're extending a chain by one. In the acetic acid ester synthesis, you always add a methyl ketone. So that's the key here, is that you end up with a methyl ketone or a total of 3 carbons added total. So you have to select, do you want 1 carbon and a carboxylic acid, or do you want 3 carbons and a methyl ketone? And so you can easily choose which one you want ahead for there. And then of course the Stork-enamine reaction works really well because you're forcing it into that trapped enol. And so the alkene can only reach out once and grab at what it's going to react with. And therefore you only get monosubstitution. And that's the really selective part of the Stork-enamine. All right, questions on that? I'm going to go ahead and stop sharing that and pull up something on my iPad here. There we go. And okay, so let's see, no other questions in the Zoom chat. Okay, I'm going to open it up for questions, and then if there are no questions, I'm going to go to the aldol condensation and use an unsymmetrical ketone and show you that we can get a variety of products depending on where we remove the proton. So that is going to be my next thing to do, show you why we like to do things like the crossed aldol reaction, because we can control the products much, much better. Okay, so go ahead and if you have questions, chime in or go ahead and put them in the Zoom chat room there. I'm going to go ahead and share my screen with my iPad here. Okay, all right. So on this exercise here, what I want to do is I want to show why we want to do things like the cross Claisen or the crossed aldol reaction. I have a question here. On the manic reaction, is there supposed to be an N in the product? Yes. In the manic reaction, we're adding a CH2 and a nitrogen compound to it. Is it not on the table here?
No, I looked on the slide and the nitrogen wasn't there.
Oh yeah, you're right. The nitrogen is not there. There should be a nitrogen between those two R's. Yes, there should be a nitrogen there. So we should end up with a tertiary amine in the product. So we have a keto compound and a tertiary amine in the product. So yes, you are right. There should be a nitrogen there. I guess it kind of got hidden when I did the bolding. I will correct that as well. And I'll send out version 2. Thank you. Okay, so let's go ahead and talk about the aldol condensation specifically as it relates to ketones, okay? So, and if we had a symmetrical ketone, like this right here, and we did our aldol condensation, we know that it's going to deprotonate this hydrogen, and then it's going to react to give us our product, which will be, let's see, we'll still have our carbonyl compound, and then we're going to have an alcohol. And so our, let's see, where are we? Yeah. All right, let's do it stepwise so everybody can see. All right. So if we just have a symmetrical ketone like this, and we create our enolate ion, negative here. So we have one of those, and it's going to come around and it's going to interact with a neutral species like this. It's of course going to attack the carbonyl compound to give us our intermediate, which is going to be OH, like this. Okay, so in our symmetrical compound, we're going to get to this kind of species, and then if we heat it, we can of course eliminate the OH and end up with an alkene from it. But let's not heat that up. Let's just look at that. So with this is a simple symmetrical place, we end up with pretty much one product before we do our dehydration. Okay. Now, what if our ketone is not symmetrical? Then we have an issue, okay? And that's where we want to think about using our crossed aldol condensation or addition reactions for that. So let me, instead of having this, let me draw just a, instead of having that acetone, that symmetrical dimethyl ketone, let's do this one instead, okay? So this is where the problem comes in, because there is very little difference between deprotonating here and deprotonating here, okay? This one is slightly kinetically favored because we have a little less sterics and we have 3 acidic hydrogens on that one. This one is a little more sterically hindered, but there are still 2 acidic hydrogens at that position, okay? So if we have attack at one position or the other, we're gonna end up with different products, okay? So let me kind of show you how that would work by, first, I'm gonna take our material here, and I am going to make our enolate at this position first. And so I'm gonna draw the product of that reaction from that one. So if we have that and it comes in to our neutral ketone species here, and we have attack by that neutral ketone species, we will end up with our OH, methyl, and then our, put that in the wrong place. This would be one of our products. Okay. Do we see where this enolate is attacking here? And so we have an ethyl group, a hydroxy, and that material. So that would be one possible product, okay, if our enolate formed in that position, okay. So what if instead we formed our enolate on the other side? Let's go ahead and draw that one attacking. So let's have our carbonyl compound down here. And if we drew our enolate and it attacked here, we would end up with our OH up here, our ethyl group there, our carbonyl over here and down here. So do we see that this compound is different than this compound because we have higher branching content? Okay. So if we went through and go ahead and did our heat to remove our water, we would end up with a product that looks like this right here. And if we heated the other product here, we would end up with our double bond forming here, and we would end up with that product here. So note, in both cases, we end up with a conjugated carbonyl compound. However, we're going to get a mixture of all 4 of these products in there because because we cannot selectively choose which of these protons are going to remove. Okay. Now, especially if you use the ethanolic or the alkoxide or the hydroxide, there is no specificity of which of those hydrogens it removes. whether it's the one on this side or the one on that side, we cannot tell. So it's going to give you a mixture of products, okay? So that's why when we think about doing the Claisen reaction, or I'm sorry, the aldol reaction as a cross aldol, we want to make sure we have one substrate that only has one kind of alpha hydrogen, and we want to make sure that the other substrate only has a carbonyl and no alpha hydrogens. That's why the cross aldol works so well, and it gives you a single product from the reaction mixture. Okay, questions on that? Correct. Since there's already base in the solution, we used alkoxide or an hydroxide to create our enolate. We already have base in the reaction, so all you need is heat at the end of the reaction. So if the reaction runs a little too quickly, you're ending up with a little bit of elimination anyway. So yes, now if you do run it where you end up acidifying it or using up all your hydroxide, you do have to add an acid or base at the end. But typically there's enough base left over in the reaction to catalyze our dehydration. Is it catalyzed or consumed? The base is actually consumed, yeah. All right, so that's one of the things that I didn't say before when we were talking about the fact that why we choose the cross aldol, but that gives you an idea of why. Let me go ahead and stop sharing and ask, are there any questions related to this? Chapter 18, chapter 19? Okay, so I like that we did chapter 18 and 19 at the same time, in the same week, because you should see common threads going through there, the creation of the enolate, the series of the acidity of the different materials. Okay, before we break, before our activity, I want to hit the top 3 things in chapter 18 and the top 3 things in chapter 19. So let me go ahead and share my screen once again. Okay, so in chapter 18, the first thing we need to find is our acidic hydrogens, okay? So we need to remember there's a reason those are acidic. The reason they're acidic is the inductive pull from the carbonyl compound. So the more electron withdrawing, the more it will be, the more acidic it becomes, okay? Now, the other reason that it is stabilized as an anion, because you have resonance, right? And remember, resonance is all about moving electrons only, okay? Resonance is moving electron only. Keto, enol, tautomerism moves a hydrogen. So tautomerism is different than resonance, okay? So the first thing I want to make sure you know, that is the most important thing is this acidity scale of alpha hydrogens, okay? And so this acidity scale of alpha hydrogens should be a logical thing in the fact that the more electron withdrawing you have, for example, the most electronegative carbonyl compound makes the thing more acidic. So that's why we have this trend going from this amide all the way down to the aldehyde as it getting more and more acidic because there is more and more, there's more and more positive charge, partial positive charge on this carbonyl. There's fewer things donating electrons to that carbonyl that would detract from it, pulling electron density away from this methyl group here. Okay. And so if that's the effect of just one carbonyl, then the same effect is seen with 2 carbonyls. Notice the esters here are less acidic than the cyanos that are less acidic than the keto ester, which is less acidic than the diketone, Okay, so as you remove electron donating groups from the outer edges of your carbonyls, it gets even more acidic. Okay, so why those hydrogens are acidic and how you increase acidity by adding more electronic groups. That's number one. Okay. And then I already mentioned number two is that the eno-keto is not resonance. Resonance is just moving electrons. The eno-keto, we are moving a hydrogen. That hydrogen is moving from this side to that side, and therefore it is its own word, tautomerization. But there is an equilibrium in this. One is more stable than the other. But if you have 1/10 of 1% of this in a reaction, and it can react with things that are electrophiles, it will. And that's how we know it's there. Even though there might be a very, very small amount of this in there, the fact that it'll slowly cascade to products tells us that it is there. And one of the other ways we know that we have this eno-keto tautomerization is the racemization or the mixing of chiral centers if they're adjacent to the carbonyl. Okay, so that's just one example that we have that this eno-keto tautomerization happens with acid or base. But the other one is that if you have something in that this double bond can react with, it'll come out and reach at. And then even though you only had a little bit of it, it'll continue to make product and product and product until all of the ketone is consumed. Okay, so that's number 2 in chapter 18. Okay, acidity and eno-keto tautomerization. And the next is our enolate. The formation of our enolate is our key step here because we use this enolate in all of our reactions in chapter 19, okay? Our enolate is this resonance stabilized form where we have a negative charge on oxygen in resonance with a negative charge on carbon. Now, when that negative charge on carbon creates a new carbon-carbon bond, that's a very irreversible bond, and therefore most of the products we see from reactants with enolates are new carbon-carbon bonds formed at that alpha carbon. That's the third most important thing about chapter 18. All right, questions about the 3 most important things in chapter 18? I think we're doing good for time. I want to talk about the 3 most important things about chapter 19. There we go. Okay. So the first thing is the difference between the different named reactions, okay? Claisen is esters, aldol can be aldehydes or ketones. And the, excuse me, in the conjugate addition reaction, it can be the Michael reaction, that's it. Okay, so they are different things, okay? So we have different starting materials, okay? So Claisens are always esters, aldols are aldehydes and or ketones, and then we have that. We have the opportunity to do cyclizations with them, but the basics are that we have esters for Claisens, alcohols and ketones for aldols. Okay. The next most important thing is there's a difference between the condensation reaction. The condensation reaction always removes a byproduct like ethanol, water, or methanol. Okay. The addition reaction gives us a tetrahedral center. Now we can go on and make it into a condensation reaction, but the fact is that the aldol can stop at that addition reaction. And then if we heat it with acid or base, we can move on to the condensation reaction. So the functional group changes the name, and the whether or not it extrudes or just adds tells us whether it's a condensation or an addition. Okay. So just like the conjugate addition reactions, we're adding to it, but we're not taking out a small molecule. Okay, so that's a very clear distinction between the different reactions. Okay, and the reason that we get things like the substitution reaction, the driving force for whether it's an addition reaction or a substitution reaction is all about leaving group, okay? In the clays and condensation, we always get that, we regain that carbonyl compound because we have the alkoxide or the water as our leaving group. It's a good leaving group, okay? In the case of our aldol, we have hydride and carbon as our leaving groups, and those are poor leaving groups. So it's all about leaving group. And that's why within the claisen or the aldol, if you do a cross system with an acyl halide, you will actually end up getting that acyl substitution because you have a good leaving group in the chloride ion. You have a good leaving group in the alkoxide ion. You have a good leaving group in the OH. Okay. And the last thing really is cyclizations. And we're going to hit cyclizations really hard in our activity. I'm going to show you my almost foolproof 5-step method for always creating the correct cyclized product in our system. So, any questions on that? Okay, we're pretty close to 12:50, which is about when we usually break. So I will stop sharing here and open the floor to questions. I'll go ahead and stop recording and we'll just post this and you can ask questions until we break completely.